In this video, we'll begin to talk about semiconductor electronics. This picture shows the crystal structure for silicon. Whenever elements combine, they generally do so in such a manner as to have 8 valence electrons. A silicon atom by itself has 4 valence electrons, so its crystalline structure is such that there will be 4 adjacent elements, or atoms, excuse me, and they share electrons. So the result is that, as you see here in this diagram, the center silicon atom has 8 valence electrons, effectively has 8 valence electrons, because it's sharing 1 from each of its 4 neighbors, plus its 4. A silicon crystal like this does not conduct electricity because the elements, or the electrons, are all bound. Now, impurities can be introduced into this crystal, and that's called doping. So the effect is different for different dopants. We'll see here, if you use boron as the dopant, boron has 3 valence electrons, and so there is a spot in the crystal where there is a hole, where there's an electron that's missing in a way. It's wanting an electron. And so a free electron can come and fill in that hole. And so if we just have silicon and boron in this crystal, then there will be holes through the crystal. And if an electron comes to fill this hole, then that means that a new hole has been created somewhere else. So in that case, when the hole is moving, that's said to be the charge carrier. So it's a positive charge carrier. So we say the hole is moving. And that's P-type silicon, because it's a positive charge carrier. And then there's also N-type silicon. So for example, you could dope the silicon crystal with phosphorus, which has 5 valence electrons. So now there's an extra electron. And this electron can move and so then that would be a negative charge carrier that's moving. So this is N-type silicon. And this doped silicon can be a resistor or a conductor. So these can conduct electricity. And the resistance level depends on the level of doping and also the type of dopant. Electrons conduct charge more easily than holes do. So electrons are a charge carrier that move more easily than holes. Whenever we put P-type silicon adjacent to N-type silicon, we get a p-n junction. This figure shows a p-n junction. So here we have this P-type silicon with the holes as the charge carriers, the positive charge carriers, and then the N-type material where we have the negative charge carriers. So where the two meet, the negative and positive charge carriers come together and form a neutral layer. So this is not a conducting layer, and it's called the depletion region or depletion layer. And this is what's known as a diode. So whenever we have a p-n junction, it forms a diode. Typically this p-n junction is on the order of 10 to the minus 6 meters thick. So let me talk now about diodes a little bit more. So again, in a diode we have P-type silicon and N-type silicon. So here's the positive charge carriers, and in the depletion region, and the negative charge carriers on the N-type. So we got P and N. Or this can also be represented like so. And if we apply electric potential to this diode, then it behaves in one of two ways. So if we apply a positive voltage to the P-type substrate and a negative voltage to the N-type substrate, then the positive voltage repels the holes and attracts the electrons, and the negative repels the electrons and attracts the holes. So we get a flow of electricity, of charge carriers. That is, if the potential here, the voltage, is high enough to overcome this depletion region. So if the voltage is big enough, then it'll push electrons through the depletion region into the P-type substrate, and then current will flow. So that's known as forward bias. And the symbol for a diode looks like this, and so forward bias would be connecting it that way. So when it's forward bias, the holes go towards the depletion region, electrons go towards the depletion region, and the applied potential causes a current flow. And then the other way of applying a potential would be reverse bias. So now we're giving a negative voltage and a positive voltage, negative to the P-type, positive to the N-type. So now electrons are attracted this way and the holes are attracted that way, so the depletion region actually grows. And in that case there's no current flowing, and so that would be reverse bias. So for forward bias, the current flows like that, and then for reverse bias, there's approximately zero current. On a diode, we have an anode and a cathode, and so that's referring to when it's forward biased, the anode is the side that's connected to the positive voltage, and the cathode is connected to the negative voltage. So anode and cathode. Oops. So anode, cathode. So here's a curve showing approximately the relationship between voltage and current in a diode. Starting off at 0 volts, the current is very, very small until we get to about 0.6 volts. And then it starts to increase, or the resistance of the diode decreases. And so then current increases dramatically with increasing voltage. And so the intersection of the tangent here and the voltage would be the threshold voltage. And it's usually about 0.7 volts. And then if we reverse bias the diode, so we get a tiny bit of current, you know, in the nanoamp range or microamp range, and that's called leakage current. Try to make this a little bigger so you can see it better. Whoops. Okay, leakage current. And then once we get to a certain voltage, all of a sudden we get a bunch of current. So we get current flowing through the diode in the reverse direction. And that's called avalanche current. And it takes place at the breakdown voltage, which is usually about minus 100 volts. So if we reverse bias a diode about 100 volts, then it'll start allowing current to flow through. So that's the, approximately the real behavior of a diode. But we approximate that. So ideally a diode, so this is the current through the diode, ID. So an ideal diode would just act like a one-way switch. So we would have no current when it's reverse biased, and then as soon as it became forward biased, we would allow, there would be no resistance. So that would be ideal. And so the real diode approximation is sort of a blend of the real behavior and the ideal curve, or ideal behavior. And so we say that there's no current until we reach threshold voltage, and then at that point there's no resistance. So this is the real diode approximation. So in our applications, we will just consider a diode to have this behavior. Infinite resistance for voltage less than the threshold voltage, and then past that, there's just a constant voltage drop. So we'll look at that a little bit more. This is for a silicon diode. There are other types of diodes. A common one is the Schottky diode, and it has advantages and disadvantages. So for a silicon PN junction diode, we have a typical voltage drop of about 0.7 volts, but a Schottky diode has a lower voltage drop, like about 0.15 volts. And a Schottky diode is a lot faster, turning on and turning off when the voltage changes. It stops current flow faster than a PN junction diode. So here are some applications for diodes. Let's see, first of all, rectification. And that's when we convert AC to DC. So for example, we have this AC voltage source. If we had a diode in series with a resistor, then our voltage here, we'll call it V out. So here's Vs, be sinusoidal. And then V out is just the top half of that waveform. So diodes can be used in DC power supplies. So you can get a signal like this using diodes, and then you can use capacitors to reduce this ripple here. So you could end up with a smoother output if you use a full bridge rectifier. And so that's what's in a DC power supply. Another application for diodes would be protection for inductive loads. So protection when using inductive loads. For example, a solenoid, which we're familiar with from our pneumatics when we have solenoid valves. So here's my drawing for a solenoid, and we have a conductive coil in the solenoid, and then there's that plunger. And so whenever current goes through the coil, which is an inductor, it generates a magnetic field moving the plunger. So here's a circuit showing an inductive load. Another example for an inductive load would be a DC motor. So say we've got a switch here. So when the switch is closed, there's high steady state current. Because an inductor opposes changes in current. So at steady state, we'd have low voltage. So here's the equation for voltage in an inductor. So it's the inductance multiplied by the time rate of change of the current. So voltage is the inductance times the time rate of change of the current. So what that means is, in this application, if we reach steady state and there's a lot of current going through here, then we suddenly open the switch. Well, now our current has, the time rate of change of our current is really high, and so we get a really big voltage spike, which can be around 300 volts. So here's time and voltage. So we could see 300 volts. Which can cause arcing across our switch, and which could damage the switch. And so what we can do, so if this switch was open, there could be arcing there. So what we can do is add what's called a flyback diode. So a flyback diode can protect our system from that high voltage. And we could simply modify this circuit by adding a diode in parallel with our inductive load. And so in steady state, there'd be no current going through this diode, but whenever we open the switch, then we get that high voltage across the diode, and it would allow current to flow this way. And so that reduces the voltage by enabling the energy to be dissipated in this coil. So whenever we're using an inductive load in an application, we need to be sure to include a flyback diode. And finally, since we're talking about diodes, let's just go over LEDs briefly. So an LED is a diode that emits light when it's forward biased. I'm not sure if I spelled that right. So in an LED, the intensity is proportional to the current. And typically the current is about 5 to 25 milliamps. And Also, typically will include a current limiting resistor. And common value is 330 ohms. So on an LED, we have two leads because it is a diode, and physically an LED looks something like that, and it has one lead that's longer than the other. So the anode is the long lead and the cathode is the shorter one. So one way to remember anode and cathode, which is positive and which is negative. Let's see if this helps. So that is my drawing of a cat, and a cat has whiskers that look like minus signs. So cathode is the negative side. So LEDs are used in one of two configurations. We have either common cathode or common negative side. The cathode is connected to a common voltage. So here we have input voltage and our current limiting resistor, and then an LED, and connected to ground. So the cathode is connected to ground. So that's common cathode. And so this way, this is active high. So when we turn our voltage high, the LED comes on. And then the other configuration would be common anode. So here we have VN once more, and our current limiting resistor. Now the LED is oriented the other way, and the anode is connected to a common voltage. So this would be a voltage rail, and here is our control voltage, our control signal. So now the LED is active whenever our VN is low. So when this voltage is 0 volts, then the LED is forward biased and it shines light. But whenever this is high, when it equals VCC, then the LED is off. So in common cathode, to get the LED to turn on, we set our VN high. Common anode, to get the LED to turn on, we set our VN low. And common anode is not infrequently seen in LEDs, because for microcontrollers and other semiconductor circuits, it's easier to sink current than it is to source current. So in this way, whenever we turn on the LED, we're sinking current, so current's going into our integrated circuit.